You ever wonder what kind of logic puzzles power a giant like Amazon? Well, we're about to break down a classic programming challenge that pops up in their technical interviews all the time. It's called the optimal utilization problem. Let's dive right in. Okay, let me put you in the driver's seat for a second. Imagine this. You've got two different catalogs of stuff you want to buy, and you have a very strict budget. Your mission is to pick exactly one item from each catalog so that their combined price gets you as close as possible to your limit, but, and this is key, without going over. So how would you find that perfect pair? So that little shopping problem, that's actually an efficiency puzzle at its core. It's all about getting the most bang for your buck, and in the world of computer science, they have a name for this exact challenge: optimal utilization. The core challenge is pretty simple when you boil it down. You need to find the best combination from two different lists to squeeze out the maximum possible value, all while staying inside a hard limit. And this isn't just a thought experiment. Big companies are using this kind of thinking all the time to solve huge real-world problems, like figuring out the best trucks to use for a shipment or which servers to assign to a task without overloading the system. Okay, so to actually tackle this thing, you're always going to be handed three key pieces of information. Let's take a look at our first example and see what those inputs look like. All right, here we go. We've got list A and list B. Think of each item in these lists as having two parts: a unique ID, kind of like its name, and a value, which you can think of as its cost or its size. And that third piece of the puzzle, that's our target. It's our budget, the absolute limit we cannot go over. And in this first run through, that target is 7. You know, this whole thing really just comes down to two golden rules. They're super simple. Rule number 1, whatever pair you pick, their total value has to be less than or equal to the target. No going over. Rule number 2, out of all the pairs that follow rule 1, you've got to find the one with the highest possible sum. That's it. That's the whole game. Okay, got the rules? Good. Let's put them into action and solve this first example. The plan is simple. We're just going to go through every single possible combination, one by one, to see what we find. So let's walk through this. First up, we grab the item from list A with a value of 2. We pair it with the only thing in list B, which also has a value of 2. Add them up, you get 4. Is that less than our target of 7? Yup, so it's a valid pair. We'll keep that in mind. Okay, next. We take the second item from A, the one with a value of 4. Pair it up. 4 plus 2 is 6. Still under 7, so it's also valid. And hey, 6 is better than 4, so this is our new leader. All right, one more to check. The last item in A has a value of 6. 6 plus 2 is 8. Uh-oh, that's over our budget of 7, so that one's no good, it's out. So, when the dust settles, what's the highest sum we found that didn't go over our budget? It was 6. That's our optimal value. But, and this is important, we're not quite done yet. The number 6 itself isn't the final answer they're looking for. Because see, it's not just about what the best sum is. It's about which items gave us that sum. We have to return their IDs. So where did that winning number 6 come from? Well, it came from the item with ID 2 in list A and the item with ID 1 in list B. And there's our answer, the pair of IDs 2, 1. Okay, that first one was pretty straightforward, right? But what happens when it gets a little trickier? What if there's not just one best pair? What do you do if you get a tie for that top spot? Let's find out. Here's our second example. Right away, you can see the lists are a bit bigger, and our target has gone up to 10. The rules are exactly the same, but now with more stuff to choose from, there are way more combinations to check. So as we start checking all the new combinations, something really interesting pops up. We find a pair, the item from list A with a value of 5 and the item from list B also with a value of 5. What's 5 plus 5? It's 10. That's a perfect match for our target. Awesome. But hold on a second. As we keep looking, we find another one. The item from A with a value of 7 paired with the item from B with a value of 3. 7 plus 3 is also 10. We've got a tie for first place. And this is the big lesson from this example. When you have a tie for that best possible sum, you don't just pick one and call it a day. Nope, the goal is to return every single pair that hits that top number. So in this case, our final answer is actually a list containing both of those winning ID pairs, 2, 4 and 3, 2. All right, so we've looked at a nice simple case, and we've tackled one with a tie. Let's step back for a second and just nail down a single, clear definition for what this problem is all about. Here it is in a nutshell. Optimal utilization is all about finding all the pairs, one from the first list, one from the second, whose values add up to the absolute highest sum you can get without going over the target. That definition right there, it covers everything, from the simple case to the one with a tie.
And it's so important to remember why any of this matters. This isn't just some random brain teaser, you know? This is about efficiency in the real world. This is the kind of logic that helps a logistics company pack its trucks with zero wasted space, or helps a tech giant manage its data centers. It's really all about getting the absolute most out of what you have.
So you get it now, right? You know the rules, you know the goal. But think about this. Our method of checking every single combination, that's fine for tiny lists. But what if each list had, say, 1,000,000 items? Suddenly, our simple approach falls apart. How would you solve that problem efficiently? Now that is where the really fun computer science starts. It's definitely something to chew on.